In this video, we're going to look at the concept of chemical equilibrium in chemistry. We also look at the relationship between concentration equilibrium constant and partial pressure equilibrium constant. Alright. Now, as we all know, equilibrium is simply a state in which the rate of forward reaction equals the rate of backward reaction. And again, a double head arrow is used for a reaction in equilibrium. That's, let's say for instance, I'm doing this reaction. Right, so a double-headed arrow like this is used to indicate a reaction involving equilibrium. Alright, now let's look at equilibrium constant expression. Now, equilibrium constant expression is expressed in terms of law of mass action, equilibrium constant expression Kc. Now, if you want to express this the equilibrium constant of this reaction we have here, we're going to apply the law of mass action, and it will be Kc equals the ratio of the products raised to their coefficient, right, to the reactants raised to their coefficients. So we're going to have C raised to the coefficient multiply D raised to the coefficient over A raised to the coefficient times B reactant B raised to the coefficient. Alright, so these small letters here are the coefficient of the reactants and products. So basically, the law of mass action is the ratio of the products to reactant concentration raised to coefficient in the balanced chemical equation. Alright, so note again that Kc, equilibrium constant expression, does not have a unit. Alright, so now let's look at a typical reaction and write the equilibrium constant expression for it. Let's write this. Okay, so we are given this reaction. 3 moles of hydrogen gas reacts with nitrogen gas to yield. Remember, this is reaction equilibrium. This double-headed arrow is used to indicate it. Alright, to yield ammonia, 2 moles of ammonia. We have to write the equilibrium constant expression for this reaction. So going to be Kc will be, so the ratio of the products to the reactant concentration raised to their coefficient. Alright, so it's going to be, this is the products, this is the reactant, so it's going to be ammonia. Alright, the coefficient is 2, this 2 here. Alright, over, then we have hydrogen gas, the coefficient is 3, then multiply hydrogen gas. Right, so this will be the equilibrium constant expression for this reaction. Now let's look at another example. What if this is the reverse reaction? Let's say we are given 2 moles of ammonia, right, decompose to yield 1 mole of nitrogen plus 3 moles of hydrogen gas. Alright, so this is going to be Kc will be, so this time I want it to be nitrogen, alright, times hydrogen gas to the power 3 over ammonia, right, to the power 2. So this will be the equilibrium constant expression for this decomposition reaction. Alright, note again that when a new reaction is the reverse of the original reaction, the equilibrium constant will be expressed as the K of the new reaction will be expressed as inverse of the original reaction, Ki. Alright, so take note of this in brackets. So this II signifies the new reaction, Kii the new reaction, this I the original reaction. Alright, so this is how we express it when a new reaction is the reverse of the original reaction. Now let's solve a typical problem on this. Let's write this. Alright, so look at this typical problem. It says given the following concentration, ammonia to be this, nitrogen gas to be this, hydrogen gas to be this, calculate the equilibrium constant for the reaction reaction A and B. So for reaction A, so equilibrium constant for reaction A will be, alright, so you use the law of mass action, the ratio of the products to the reactant concentration, raise the coefficient. So it's going to be, alright, so ammonia, the coefficient of ammonia there is 2, alright, over nitrogen, alright, multiply hydrogen gas. The coefficient there is 3. So when you simplify this, you just impute the values. If you impute the values for ammonia, ammonia there is probably to be 3.1 times 10 to the power minus 2. Alright. So the coefficient there is 2 over. So we're going to have nitrogen there is 8.5 this point. Alright, times 10 to the power minus 2. Alright, so the power here, does that have a power? No, okay. For hydrogen will be multiply 3.1 times 10 to the power minus 3. Alright, the power of hydrogen is 3. Alright, so let me punch this to the calculator to give us the equilibrium constant for reaction A. So we're going to have, let me wipe this place. The numerator will be, alright, 9.61 times 10 raised to the power minus 4. So break it down like, don't punch it twice, alright, just break it down like this. We have the denominator. If you punch it, it's going to give you, so we have it to be 2.532, alright, if you are living in two decimal places, times 10 to the power minus 9. Alright, so when you simplify this further, you can then punch everything together. So it's going to give, alright, so if you punch it together, you have this value 379,146, right, 0.9194. So if you leave it in standard form, it's going to be, so you move this, since you're going backward, 1, 2, 3, 4, 5, so it's going to be 3.7 times 10 is to the power minus 5. Alright, so this will be the equilibrium constant expression for the reaction Kc or Ka, rather, this is reaction A. But remember, it does not have a unit. Alright, so let's wipe down solve for the second problem. That's question B. Alright, so B part of it, equilibrium constant expression Kb will be, so ratio of the products N, so nitrogen times hydrogen, the coefficient is 3 over ammonia, so the coefficient is 2. So when you input the values, you're going to have, for nitrogen we have it to be 8.5 times 10 to the power minus 2. Alright, right, multiply for hydrogen is, we have it to be 3.1 times 10 to the power minus 3. Alright, so the power, the coefficient of hydrogen is 3. Right, so we put it here, then over that of ammonia. Ammonia is 3.1 times 10 to the power minus 2. So coefficient of ammonia is 2. So let's simplify this. Wipe some parts. So the numerator will give us 2.532. If you are leaving it in 3 decimal places, times 10 to the power minus 9. So I divide by, so the denominator will give us 9.61 times 10 to the power minus 4. So when you break everything together, it's going to give you, alright, so we have it to be 2.634. Alright, if you are leaving it in 3 decimal places, times 10 to the power minus 6. Alright, so this will be the equilibrium constant expression for this reaction B. Kb equals this. Alright, so this is it for this question. Now note that this reaction is the reverse of this. But in otherwise, when you do, let me show you, let me clean this place. When you punch 1 over this value, we got 2.63, okay, 4 times 10 to the power minus 6. Let me punch it with my calculator. So it's going to give us the first value we got for the equilibrium constant expression for reaction A. So it will give us 37965 0.7213. Alright, so when you put in standard form, that's you go backward 1, 2, 3. So you go 1, 2, 3, 4, 5. So it's going to give us 3.7 times 10 to the power 5. Alright, the same thing applicable when you do 1 over 3.7 times 10 to the power 5. You still get back to this. So let me punch it to my calculator to verify it. Yeah, correct. To give you the same value, you get back to this. Alright, so that's it for this problem. So let's wipe this now. Look at the relationship between concentration equilibrium constant and partial pressure equilibrium constant. Alright, so the relationship between concentration equilibrium constant and partial pressure equilibrium constant is expressed in this term. So Kp equals Kc in bracket out T. This is R T. Alright, changing and the mole value. So this Kp partial pressure equilibrium constant, Kc concentration equilibrium constant R is ideal gas constant. Alright, whereas the T is temperature and the N is number of moles, alright, of the reaction. Now let's look at a typical problem on this and apply the formula on it. Let's write this. Alright, look at this question. It says in the reaction, so this reaction gave ammonia the equilibrium concentration at 725 Kelvin, where these values. Alright, use the data to calculate the concentration equilibrium constant at this temperature and Kp for this reaction under the same condition. So we are given the ideal gas constant. So the formula we're going to apply will be Kp partial pressure equilibrium constant equals Kc concentration equilibrium constant multiply, ideal gas constant times temperature is the power change the number of moles. Alright, so now let's get to our Kc for this reaction. So the Kc concentration equilibrium constant will be the ratio of the products to the reactant concentration raised to their coefficient. Alright, so it's going to be, we have NH3 right to the power 2 over, so we have nitrogen multiply hydrogen to the power 3. Alright, so when you put the values, you're going to have, so we have our ammonia to be 0.095, alright, raised to the power 2 over the nitrogen. We have the nitrogen to be 1, alright, and we have the hydrogen to be 0.51, alright, so coefficients value is 3. So when you simplify this with your calculator, you're going to have, let me punch it. So you have 0.068 if you're leaving it in 3 decimal places. So remember, it doesn't have a unit. Alright, so now what we are getting Kc, we can now impute them in the formula. Let me wipe this side. Alright, so Kp equals Kc bracket out T change in N. Alright, so let's impute that Kp will be Kc 0.068 multiplied, so I think that constant is 0.0821, alright, times temperature there is 725. Right, this is bracket. Now the N will be the change in the number of moles, that the mole of the product, alright, we minus the mole of the reactant. So the mole of the product here, this is the mole value. The product is 2, Alright, we have the reactants. We have this 3 here plus the 1 here for nitrogen. So it will 3 plus 1 is 4. So we have 2 minus 4 give you negative 2. So the change in mole value is negative 2. Alright, so when you simplify this with the calculator, you're going to have AP equals, let me simplify this. So when you punch everything with the calculator, you're going to have 1.919 times 10 raised to power minus 5 if you are leaving it here in 3 decimal places, and this will be the partial pressure equilibrium constant for this problem. Alright, so it's as simple as that, guys. Now note that once change in n, alright, change in the number of mole equals 0, Kp will be equals to Kc. That the partial pressure equilibrium constant will be equal to the concentration equilibrium constant. Alright, before we end this video, I want to show you one more thing to note. Alright, so let me wipe this to illustrate it or show you. Alright, so when you have this kind of situation, this is reaction 1 and reaction 2. Alright, so when a new reaction differs from the original reaction by a common factor n, the equilibrium constant expression will be expressed like this. Alright, so what you do is that you multiply the original equation by half. Alright, so for in this case, this is the original equation and this is the new equation. So this new equation is different from this original equation by this factor of n. Alright, okay, so when you multiply this original equation by everything here by half, right, you will get back to this. Therefore, the new equilibrium constant for reaction 2, right, will be equals to the equilibrium constant for reaction 1, right, raised to the power of half. Alright, so this is what we're going to have. Alright, so take note of this. When a new reaction differs from the original reaction by a common factor n, the equilibrium expression, will yield to this. Alright, so you multiply the original equation by the common factor n. In this case, it's the common factor of n. Alright, so when you multiply the original equation by it, you will get back to this equation. Alright, so guys, this is basically the concept or idea behind chemical equilibrium in chemistry. We looked at equilibrium, so concentration equilibrium constant, partial pressure equilibrium constant. We also looked at relationship between partial pressure equilibrium constants and concentration equilibrium constants, and look at law of mass action, how to express equilibrium constant, and others. So with this, I'll come to the end of the class. Hope there's something interesting. If you're new to the channel, ensure you subscribe. For more videos, like, share, and comment on this video. Tell me if you seem to have any specific question to ask. If you leave a question in the comment section below, and I will show you the response. That's it for this class, guys. Thanks for watching.